Okay, this is sample problem 14.9. The rate constant for a particular first-order reaction is given for 3 different temperatures. So essentially 3 reactions were done, 3 experiments were done at 3 different temperatures. So the first temperature was 400 Kelvin, which is up on the upper hand left side. And the value of the rate constant K was measured, and it's 2.9 times 10 to the minus 3 reciprocal seconds. Then the temperature was changed to 450 Kelvin, and K was measured again, and this time it was found to be 6.1 times 10 to the minus 2 molar. 10 to the minus 2 reciprocal seconds. Finally, at 500 Kelvin, the rate constant was measured as 7.0 times 10 to the minus 1. So notice the rate constant gets larger every time you raise the temperature, which is a relationship which we often call the Arrhenius relationship or the Arrhenius equation. A form of the equation is shown here on the left, ln of k1 over k2. So that's the natural log of the rate constant 1 and 2. Meaning that they're measured at different temperatures in this context. So K1 is measured at T1, and K2 is measured at T2, and K3 is measured at T3. Now, if you take the ratio of these rate constants, it's equal to the activation energy, E sub A, divided by the universal gas constant, R, times 1 over the second temperature minus 1 over the first temperature. So for this one, what they ask us to do is to use the data and calculate the activation energy, or E sub A. So you have a choice. You could pick any 2 sets, but I'm going to pick the first 2 sets. Actually, you know what? Yeah, I'll do 400 Kelvin will be T1, 450 will be T2. So let's write that down. So T1 is 450 Kelvin. 400 Kelvin. Let me write that down correctly. Again, you could pick any 2 that you want. T2 is 450 Kelvin. And then K1 is the temperature, is the K, the rate constant, that's at T1. So that means that K1 would be 2.9. I'm just looking at the table here. 2.9 times 10 to the minus 3 reciprocal seconds. And then K2 would be 6.1. Just be careful, I've got a different exponent there. Okay. We just want to find E sub A. So it's just really just an issue of algebra. So if we want to isolate E sub A, I'm going to make it a little simpler. Suppose I said it was this. So suppose I said X equals E sub A over R times, I'll make this Y. And I want to isolate E sub A. One method I could do is I could multiply both sides by R. Right? And then this R would cancel there. And then I could divide both sides by Y. And then that Y would cancel. And we would just have activation energy. So it looks like all we got to do is multiply both sides by R, and then multiply both sides by whatever's in the parentheses. So it's going to be kind of, interesting looking. So I'm going to divide both sides by 1 over T2 minus 1 over T1, just like I divided both sides by Y. And then I'm going to multiply both sides by R. So R times ln of K1 over K2 over 1 over T2 minus 1 over T1. And that should give you the activation energy. Okay? Be careful when you're doing this calculation. R is 8.314, not 0.08206 as you've often seen. We're going to use joule units. So 8.314 joules per mole Kelvin. So that's R. Times the natural log of K1 over K2. So K1 is 2.9 times 10 to the minus 3 reciprocal seconds over 6.1 times 10 to the minus 2 reciprocal seconds. Then we're going to divide that by 1 over T2. So T2 is 450. So 1 over 450 Kelvin minus 1 over 400 Kelvin. Now, what's going to happen is you're going to have two negatives. One of the negatives will be the natural log, because the number in the numerator, 2.9 times 10 to the minus 3, is smaller than the one in the denominator, 6.1 times 10 to the minus 2. So you get a negative there. But 1 divided by 450 minus 1 over 400 is also going to be negative. So those negatives will cancel, and you'll have a positive value for E sub A. So I'm going to take what's in the natural log first. So I'm going to take 2.9 times 10 to the minus 3 divided by 6.1 times 10 to the minus 2. Take that ratio, which is 0.0475. Take the natural log of it. And yeah, I get negative 3.046. Multiply that by 8.314. And I'm going to go ahead and write that as minus 25.26 divided by, now I'm going to do the denominator, 1 over 450 minus 1 over 400, and you get minus 2.78 times 10 to the minus 4. So now you do that ratio, you can see the negatives are going to cancel. So 25.26 over 2.777 or 7 times 10 to the minus 4, and you get big number. You get 9.09 times, that's probably too many sig figs, times 10 to the 4. Okay, so we could probably round that to 9.1 times 10 to the 4. There's only 2 sig figs in all those numbers that we just calculated there. So let's take a look at this now. Now what about the units? Reciprocal seconds are going to cancel. This is 1 over Kelvin. This is 1 over Kelvin there. So the kelvins are going to cancel. So you're going to have joules per mole. Now, I will point out that it is common to report activation energies not in joules per mole, but in kilojoules per mole. So you just divide it by 1,000. So if I take, I'll do that over here, 9.09, I'm sorry, 9.1 times 10 to the 4 joules per mole times a kilojoule per 1,000 joules. Right? And you get it at 9.1 times 10 to the 1 kilojoules per mole. Now typically when the exponent in the power of 10 is just a 1, we just go ahead and move it over 1 and make that 91 kilojoules per mole. So there you go. There's your activation energy. And that's typically the sort of value you see for these problems. So this is called the Arrhenius equation. There's different forms of it. You'll see it written different ways. This is a nice way to do it. And again, we could have done 450 and 500, or we could have done 400 and 500. We should get around the same answer each time. It may be a little bit different. There are better methods for doing this sort of calculation. This is really just an estimate of what the activation energy is. If we wanted to get a better value, we would take more temperatures and more rate constant values and then do a graph.